Good afternoon. Hello, everybody. My name is Adilson Presoto from UFSCar, and it's an honor for me to introduce Professor Giovany Figueiredo from Universidade de Brasília, and he will talk about the existence of least energy positive and nodal solutions for quasilinear Schrödinger problems with potentials vanishing at infinity. Giovany has an impressive scientific production about different kind of problems about elliptic PDEs. It's a vast list of important works in the area. Welcome, Professor Giovany.
Thank you, Adilson, for this very, very nice introduction. Good afternoon, everybody. I would like to thank the organizing committee for the opportunity to talk about this work that was made with my friends Ricardo Ruviaro from Universidade de Brasília and Sandra Moreira Neto from Universidade Estadual do Maranhão. As Adilson said, I'm talking about existence of least energy positive and nodal solution for a quasilinear Schrödinger problem with potential vanishes at infinity. And we start with our problem. In our problem, there is a well-known operator. There is a function. A function plays an important role in our argument, and it has two potentials, V and K, that can be vanished at infinity. And a basic motivation for the study of this equation comes from the fact that it's satisfied by standard wave solution for this quasilinear Schrödinger equation. Namely, solution of this way, of this form. And in the case rho applied in S equal S, if PC is a solution of this quasilinear Schrödinger equation, U is a solution for our problem. Quasilinear Schrödinger equation appear naturally in mathematical physics and have been derived as models of several physical phenomena corresponding to various types of nonlinear term ρ. For example, the superfluid film equation in plasma physics has this structure for ρ applied S equal S, as you can see in this paper. In this another situation, quasilinear Schrödinger equation models the self-channel of a higher power ultra-short laser in matter, as you can see in this another paper. Quasilinear Schrödinger equation also appear in fluid mechanics, in the theory of Heisenberg ferromagnetics and Magnus, in dissipative quantum mechanics, in condensate matter theory, as you can see in this another paper. For more references, more physical motivation, in this paper, you can see in this paper due to Proppenberg, Smith, and Wang. After I will go back in this paper due to Proppenberg, Smith, and Wang. Okay. As I said, we are going to study this class of problems, and now you give some hypotheses in the function A, in the function V, K, and on the nonlinearity F. About V and K are continuous and are positives, and K is in L infinity. I have this another hypothesis This integral is small at infinity. Here, in this work, I consider two relations between V and K. The first one is this hypothesis, or I will consider this another relation between V and K. The hypothesis about the function A is like this. This function is positive, and it is between two positive constants. Now, I give the hypothesis on the nonlinearity F. The first hypothesis is if I have this relation between N and K, I have that this limit equals 0. Or, if I have this another relation between V and K, I have that this another limit is equal 0. And the nonlinearity has these grounds at infinity. In fact, if it has a quasi-critical grounds at infinity, the nonlinearity satisfies the classical Ambrosetti and the Rabinovich condition. And finally, the nonlinearity satisfies this hypothesis. And this hypothesis is equivalent to say that this function is increasing, is strictly increasing for t in this interval. In order to give the main result, let's consider this set. Note that this set is not a vector space. It is an important information for us. X is not a vector space. And now I define a weak solution for all problems. A weak solution for all problems is a function u in this set. And pay attention, please. X is not a vector space. And you satisfy this equality for all v in this space. A weak solution is called a ground state solution if its energy is minimal among all non-trivial weak solutions. The main result is like this. With this hypothesis, our problem has a positive ground state solution and a nodal ground state weak solution, which has, in the last case, the nodal solution has precisely two nodal domains. Okay, the class of problems like this one has been extensively studied during the last years via variational methods. Consider essentially two techniques. The first technique is to work directly on the associated functional in spite of its lack of smoothness. To the best of our knowledge, the first existence result involving this approach was obtained in this paper due to Proppenberg, Smith, and Zhi-Qiang. The first approach for this class of problem is to make a change of variable. For example, in this paper, the authors use the Estadual approach to reduce the quasilinear equation to a semilinear one and using inner elliptic space framework. For more recent results to this quasilinear Schrödinger problem involving change of variable, you can see in this list Corinne Jean, Claudio Alves, David Costa, Olímpio Miyagaki, from UFSCar, Shen, Wang, Sheng, Xuanxi, Sheng, and Jia-quan. I have another list, Ed Carlos Silva, Jefferson Silva, Xiandong Jianshun, Mimbo Yang, Carlos Alberto Santos e Joe. Two last colleagues is they are professor here in Universidade de Brasília, Champ, Xifeng, and Aran, for example. But since in our program the function A appears in front of this term, the change of variable cannot be considered here. So I use I'm working directly with the function, the associate functional our problem. So therefore we work directly with the functional associate with the problem. Some remarks. The set where I'm going to look for solution is not a vector space. It's a big and good difficulty for us. Another remark is the associate functional is not differentiable. More remarks. In this work, you show existence of positive nodal solution for our problem. However, you consider class of potential V that is not considered in the paper do two Proppenberg, Smith, and Giovany. In order to overcome the lack of compactness, we use a result that can be found in Caldono Alves and Marco Aurélio Souto. However, due to the presence of this term, it was necessary to extend the range in which compactness occurs. Now, I start to give a sketch of the proof of our result. Let's consider, I would like to remember this Hilbert space. With this Hilbert space, I define this another Hilbert space. This space with this norm is a Hilbert space. And you define the functional J, not that the functional J is not differentiable, and it was defined in the set X that it's not a vector space. Not that the functional J is not Frechet differentiable, but it's there exists the Gateau derivative for this functional one, okay? And the Gateau derivative is like this. With this definition, let's define this Lebesgue space. Now, here I have the compactness result. The compactness result is like this. If I have this weak convergence and if this sequence is bounded, I have this strong convergence. Okay, this is a compactness result, and this result, of course, was inspired in Alves and Souto's paper, and it is a consequence of the hypothesis on the potential V and K at infinity. However, I repeat, due to the presence of this term, it was necessary to extend the range in which compactness occurs. Now, I will give a sketch of the proof of the first part of the paper, né? This positive solution case. For this, I define, I give this another hypothesis on the linearity F. I define the linearity set for our functional J, for the associate functional J. Note that in this definition, I'm considering the Gateau derivative, not the Frechet derivative. And as a consequence, here, the Nehari manifold, the Nehari set, is not a manifold. So, but ever there is a unique projection dysfunctional in the Neharry set, and the proof is this one. I define the functional J like this, using the grounds about the nonlinearity. I have this inequality. Using the classical Ambrosetti and Hamilovich condition, I have this inequality. And I conclude that for T small, this function is positive, for T large, then this function is negative. So, there exists T0 such that this function achieves this maximum. So, there is a projection, and this projection is unique because if there exists another parameter such that this function is in the Neharry set, I have these two equalities. Since this function is increasing, I conclude that T0 is equal to C0, and in this case, I have the unicity of the projection on the Neharry set. Another result says that all the sequence in the Neharry set is far from of the origin. Once more, I use the relation between V and K, the grounds about the nonlinearity, and I obtain this inequality, and with this inequality, if F is small, I have this inequality. And with this inequality, I prove that all the sequence in the Neharry set is far from of the origin. In the next result, you prove that the minimized sequence is bounded, and is bounded in E, and is a consequence of the fact that this function is increasing. Using the hypothesis 4, I prove that this function is increasing, then I have that this sequence, the minimized sequence, is bounded. Okay? Now, I prove that this term, this sequence is weakly Laurent semi-continuous. For this, I consider the classical Ambrosetti and the Rabinovich condition. I use in here that this classical Ambrosetti and the Rabinovich condition, and conclude that this sequence is bounded in L1. As a consequence, this another sequence is bounded in L2. Moreover, I have that since the sequence is bounded in E, and I have space up to sequence, I have this weak convergence. I have compact embedding here. I have this strong convergence. And with this strong convergence, I conclude that this sequence is bounded in L2 too. So I have that this sequence is bounded in L2. This another sequence is bounded in L2. I conclude that this sequence is bounded in E, and up to a subsequence, I have this weak convergence in E. Now I'm using here derivative in the distributional sense, and I conclude this equality. More in calculations allows to conclude this weak convergence. Now, since this function is continuous and convex, I conclude that this sequence is weak Laurent semi-continuous, and since A is positive, I conclude that this another sequence is weak Laurent semi-continuous, and the result follows. Now, I prove that the infimum of the functional way restricting the Nehari set is achieved. I consider minimized sequence. It's bounded in E, and the aperture sequence I have this weak convergence. Now, I can conclude that this weak limit is non-trivial, because otherwise, I have that, since I have this strong convergence, I have this inequality, and this things converge to zero, is a contradiction, because in previous lemma, you prove that all the sequences in the Nehari set cannot converge to zero. So, the weak limit is non-trivial, so I can make the projection in the Nehari set. Now, I use that the norm is regular semi-continuous. I'm using here the compactness result. I conclude that this point, in fact, achieves this minimum. So, there is a minimum for the functional, for the associated functional when restricted the Nehari set. Now, I will prove that this minimum point of this functional when restricted the Nehari set, in fact, is a critical point of the functional one in all space. Here, this argument is due to Proppenberg, Smith, Zhi-Qiang, and is an argument by contradiction. Suppose that this infimum in the Nehari set is not a weak solution for all problems, then I find this point in this space such that I have this inequality. Okay? With this inequality, I can consider T is sigma in this interval such that I have this another inequality. Pay attention, please. I'm not using that the functional J is differentiable, because the functional J is not differentiable. I'm using here that the fiber map that depends on T is sigma is continuous. For this, I have that this inequality for T and sigma in this interval. I define a special cutoff function, and now I will take some estimates about this value. For T in this interval, I have this inequality. For T in this interval, using some computation here, I have this inequality. And for T equal 1, I have the sum inequality. So, in all the cases, I have that G supremo is less than C. C here is the infimum of the functional J when restricting the Nehari manifold. Note that if you find some T such that this point is in the Nehari set, I have a contradiction, because this U is the point that achieves the infimum of the functional J when restricts the Nehari manifold. For this, I define this function, upsilon function. Note that if I find a point in this interval such that the functional upsilon in this point vanishes, I have that this point is in the Nehari set, and I have a contradiction. Note that upsilon in this point is positive, upsilon in this point is negative. Since upsilon is continuous, there is a point in this interval such that upsilon in this point equals 0. In other words, I have that this point is in the Nehari manifold, and I have a contradiction. And if I have a contradiction, I conclude that the minimum point in the Nehari, the minimum point in the minimum point on the Nehari of the functional when restricted in the Nehari manifold is in fact a critical point of this functional one in all space. Now, I'm talk about nodal solution, and I start defining the weak, the nodal solution or sigma change solution. Weak solution is a point in X such that positive part is non-trivial, negative part is not trivial, that satisfy this equality for all V in this space. In particular, you look for U in X, which has exactly two nodal domains or equivalently. Change signal exactly once. You look for a point in the Nehari nodal set that achieves this mean, and the Nehari nodal, the nodal Nehari set is this set. Okay, of course, it's not a manifold. And I'm using here this notation when I want to consider the positive part in the negative part, and the first result is the functional J is cohesive when restricted in the Nehari set, and all the sequence in the Nehari set is far from of the origin, and the sum result is true when I consider sequence in the Nehari nodal Nehari set. And the proof is this one. I'm using here that this function is increasing, and since this function is increased, I conclude that the functional when restricted in the Nehari set is cohesive. And in order to prove that all the sequences is far from of the origin, I consider these grounds or these another grounds about the nonlinearity F, and you obtain these two inequalities, or these inequalities or this another inequality. And I'm using here the definition of the Nehari set, and considering the first relation between the K, I have this inequality. Since this exponent is greater than this exponent, I conclude that all the sequences minimized in the Nehari set is far from of the origin. But if you consider this another relation between the K, I have this inequality. But here, this exponent is greater than 2, this exponent is greater than this number. So I conclude the sum result. All the sequence in the minimized set is far from of the origin. For the case nodal Nehari set, the proof is the same because this set is intermediate in this set. So the sum is true for all sequences in the nodal Nehari set. Okay. Note that since the minimized 6 does not converge to 0, and use the grounds on the nonlinearity F, if this sequence is in this nodal nonlinearity set, I have that this limit is positive. Is a direct calculation. So, in the case nodal solution, I have that there is a unique projection in the nodal nonlinearity set, and it's a consequence of the support of positive part of U and negative part of U are disjoint. The proof is similar of the previous result. So there is a unique projection in the nodal nonlinearity set. Now I sketch of the proof. Let's start with the existence of a minimizer in the nodal nonlinearity set. C0 for us is this infimum. And the by lemma 9, C0 is positive. And there exists a bound minimized 6 in the nodal nonlinearity set, because J is cohesive when restricted in this set. So the minimized 6 is bounded. So I have this weak convergence em I, weak convergence and strong convergence in this Lebesgue space, because I have strong convergence, I have compactness result, and use this continuous embedding, I have this another strong convergence. And using a well-known argument, I conclude that this strong limit, in fact, is the positive part and the negative part of the strong limit. Since I have strong convergence, I have this convergence. Since this limit is positive, I conclude that the W plus and minus is non-trivial. As a consequence, I have that this strong limit is sigma changing. So, if this limit, strongest limit is sigma changing, I can make a projection in the nodal nonlinearity set like this. And since this norm is weak law is semi-continuous, since I can use this strong convergence, I conclude these two inequalities, and with these two inequalities, I conclude that T and S, the projection in the nodal nonlinearity set, is less than 1. I use this fact in order to show that this point achieve C0. Now I'm using that this calculation, this direct calculation, and I can conclude that this point achieve C0. In fact, it's possible to show that T equal S and equal 1. In this case, C0 is achieved by W, and W is a sigma change. At this point, you show that this point that achieve the mean of the functional day when restricted in the nodal nonlinearity set, in fact, is a critical point of the functional day in all space. In other words, W is a weak nodal solution for all problems. Once more, I'm using an argument due to Smith, Lebesgue, and Wang's. The argument is by contradiction. If U is not a weak solution for our problem, there is a function in this space such that this inequality holds. For T, S, and sigma in this interval, I conclude this inequality. Pay attention, please, once more. I'm not using that J is pressure differentiable. In fact, I'm using here that the fiber map is continuous. Fiber map is continuous. I'm using, in fact, that the J is Gateau derivative, just Gateau derivative. And I define that cutoff special function. And once more, I take some estimate about this value. For T and S in this interval, I have this inequality. For T and S in this another interval, I have the sum inequality. For T equal 1 and S equal 1, I have the sum inequality, and I conclude the estimate, this estimate. Once more, if I find a special T and a special S such that this point is in the nodal Néhari set, I have a contradiction. For this, like this, if I find T and S, T overline T, overline S, such that if this point in the Néhari nodal set, in fact, I have a contradiction. But it's sufficient to show that this point in the Néhari set, because if it is in the Néhari set, it is a nodal Néhari set. For this, I define the function upsilon like this. Note that upsilon in this point is positive, in this another point is negative. So there exists a pair in this interval such that upsilon vanishes this point. So I conclude that this point in the Néhari set, and the result follows. Finally, you prove that the nodal weak solution has exactly two nodal domains, or equivalently, it changes sigma exactly once. It's a well-known argument. If W, I can prove that W is continuous, this set is open, and suppose by contradiction that W is like this. W has three components with these properties, and I'm using here that these points that are supports disjoint. I'm using here that this W is a solution for our problem. I have this equality. Now I make projection in the Néhari set for these points, and as a consequence, I have this inequality. So I have this contradiction. This contradiction because this point in this Néhari set is strictly less than C0. Então, I have a contradiction, and I conclude that the solution sigma change once. And the proof of our theorem is complete. And to finally, I would like to show only last remark. This remark is the functional associated with this class of problem only has negative derivative. Since it is not differentially differentiable, técnicas envolvem palês meio ou theorem ciclos in the classical sense cannot be used in this class of problem. It is a big and good difficulty when we study this class of problems without change of variable. So, thank you very much, my friends of UFSCar, and congratulations for this very nice meeting.
Thank you, Giovany, for the very nice talk. Now we have some time for the questions from audience. While they send the questions, I have one for the function because you consider the function a positive, and you see that is essential for control the norm. Yeah, it's possible to do something when a vanishes in a positive set, in a set with a positive measure.
A good question, Adilson. A good question, but maybe I don't know to answer. But I would like to say is the following. Claudio No Alves has a paper that studies this class of problem, and in that paper, he considered a constante that this constante quem assume negative signal. That for this, I think that if you take the function A is signal change, since L infinite norm is small, I think it's possible to show the result. But I cannot to claim about this, okay? I think this result is possible to be true.
Okay, great. You have some time for some question if you have. Let me see on the chat. I don't think you have no more questions. I want to apologize. No, sorry. Thank you again, Giovany, for the excellent lecture. And you'll see very soon here at UFSCar with us. And very thanks again, Giovany.
Thank you, Adil. Very much.
And I have a announce to do before. Uh, we would like to inform you that the lecture of Professor August Ponce has been rescheduled to 15:30 local time before the closing the workshop. So you have some extension of schedule today, but we hope you continue with us, and we warmly invite you to join us just the end of the new schedule. So you see you at the next lecture from Marcos Pimenta in 15 minutes. So bye, and you see you. I see you in the next lecture. Bye bye. Hello, everybody. We are back, and now it's an honor for me to introduce Professor Marcos Pimenta from Universidade Estadual Paulista at Presidente Prudente, and he will talk about on a quasilinear elliptic problem involving the one biharmonic operator and a Strauss type compactness result. Marcos' interest lies mainly in variational methods applied to elliptic PDEs. In particular, he has contributed recently to the understanding the one Laplacian operator in the BV space framework. Welcome, Professor Marcos Pimenta.
Okay, Adilson, thank you very much for the kind introduction. And now I'm going to talk about a joint work with Professor Olímpio Miyagaki, which is our great friend, and also together with Elardo Juarez Hurtado. Okay, in this work, first of all, I kindly would like to thank by the kind invitation and by giving me the opportunity to deliver this talk here. Okay, it is a great pleasure for me, indeed. Okay, in this work, I'm going to talk about on a quasilinear elliptic problem involving the one biharmonic operator and a Strauss type compactness result. Okay, this problem, in fact, it has been inspired by a similar one which we have made together with Professor Giovany Figueiredo, dealing with the one Laplacian operator. Okay, then first of all, let me talk you a little bit about the one Laplacian operator. The one Laplacian operator, it is a quasilinear elliptic operator which arises, for example, when we try to do some image restoration procedure, okay, in fracture mechanics and some others applications. And in fact, when we deal with problems involving the one Laplacian operator, in general, we are led to deal with this sort of problem in the space of functions of bounded variation, okay, which is the BV space, which is a space a little bit wider than the W11 space, okay? And of course, this operator has a lot of interest from an application from the applied point of view, but also from the mathematical point of view, because when we deal with this sort of problem in the space of functions of bounded variation, a lot of difficulties arise, which in general makes our life hard to just generalize the methods which are used to apply to P-Laplacian problem, to usual Laplacian problem, okay? Okay, as far as image restoration is concerned, besides the usual method, which is based on the minimization of the integral of the gradient of u to some power, okay, which is widely used to these people which are used to do this sort of procedure, you can also, for example, try to mimic this kind of method by trying to minimize energy functionals which have in the place playing the role of the gradient of u. Instead, you have the total variation of the Laplacian of u. Okay, for example, in this paper, which is a paper from 3 people, okay, if I remember, it is Osher, one of them. I don't remember clearly. But in this paper, they have they studied the minimization of this, the minimizers of this functional. And they have compared these minimizers with the analogous functional, putting in the place of the Laplacian of u, the modulus of the gradient of u. Okay, then they perform some kind of comparison between the 2 methods in order to see which one is better in one or in another situation, okay? Then this is just to say you that this kind of problem in which you have the integral of the total variation of the Laplacian of u, it is something which have some interest from the applied point of view also, okay? Very good. In general, when we deal with this sort of functional in which you have the total variation of the Laplacian of U, you are led to consider quasilinear elliptic problems involving the so-called 1B Laplacian operator, okay? The 1B Laplacian operator, which is an operator formally defined by this way, okay, it is the Laplacian of U divided by the modulus of the Laplacian of U, okay? In the same way that the 1 Laplacian operator can be seen as how can I say, a case of the P Laplacian when P it is equal to 1, in the same way you can see the 1 biharmonic operator as a special case of the P biharmonic operator, okay, which is much more studied than the version in which you have P equals to 1, okay? For example, you can see this sort of operator when you study some kind of systems involving the usual Laplacian operator. In some cases, you can reduce this system to just a single equation with the P biharmonic operator, okay? Very good. Okay, as far as problems involving the 1 biharmonic operator, up to my knowledge, the very first one to deal with this sort of problem, it was Enea Parini, Bernard Ruff, and Cristina Tarsi, okay? In which they have studied, in 3 papers, in fact, they have studied something about this operator. The first one, it was this one in which they have studied the Rayleigh quotient associated to the total variation of the Laplacian of U, okay? And they have considered this, quotient in the space BL0, okay? This space BL0, it somehow behaves as the BV space when compared with the W11 space, okay? For example, the BL0 space, it is the space of functions in W11, okay? Such that the Laplacian of this function, it is a distribution generated by a radial measure, okay? Then, of course, we can see that, for example, there are a lot of functions which are in, for example, the W210, okay? Which, of course, it is inside of this space too, okay? But of course, this space, it is much wider than, for example, the W21 of 0, okay? Very good. In the another paper, the same people, Parini, Ruff, and Tarsi, they have studied the very same Rayleigh quotient, but considering the infimum taken over the C infinity, the space of test functions, okay? In fact, since this functional space, it is not dense in BL0 with respect to the topology coming from the norm, these two numbers are different, okay? Tends to be different, and in fact, they are different. Okay, in 7, the same authors, Parini, Tarsi, and Ruff, they investigate some optimal constant of the Sobolev embedding of some spaces of functions which are associated to the 1 biharmonic operator, okay? And in fact, in all of these papers, they considered another questions, like, for example, the kind of domain which tends to minimize this constant, and so on and so forth. Okay. Then, for example, up to this, I don't know, in fact, very much papers dealing with this operator. I think that it is in a very beginning of the study of this operator, okay? Beyond these 3 papers which I told you, we have started to study this problem. And in a paper together with Professor Sara Barilli from Bari, okay, in Italy, we have studied a nonlinear version of the problem which have been studied by Enea Parini, Ruff, and Tarsi, okay? We have studied this problem here, in which we have considered something, we can say that it is an analogous of the Navier boundary condition to the usual biharmonic operator, okay? And when this function f here could have different behaviors, okay? In the first result, we have imposed some conditions on f, which says to us that it is a superlinear nonlinearity, okay, a subcritical and superlinear nonlinearity. And then we succeed in proving that there exists a ground state non-trivial bounded variation function to this problem when f is assumed to satisfy this sort of condition, okay? In the second part of the paper, we have imposed some conditions which allows f to be sublinear. And then by global minimization, we have proved that for certain values of a parameter lambda, which we put in front of the f, okay, the nonlinearity f, if this parameter is great enough, then we do have a solution to this sort of problem, okay, a non-trivial solution. Very good. After it, we okay. I would like also to cite another paper which deeply have inspired us in the present paper that I'm presenting to you now, which was a paper from myself and from Professor Giovany Figueiredo. Okay, in this paper we have in fact proved the compactness of the embedding of the BV-rad. Okay. The BV-rad is the space of functions with bounded variation, which in Rn, which are radially symmetric. Okay, we have proved the compactness of the embedding of this space in some Lebesgue spaces, like for example LQ for Q between 1 and n over n minus 1. Okay, and then we have done, of course, in order to do it, we needed to show a kind of Strauss radial lemma, okay, a version of the Strauss radial lemma to the space BV. We succeed in doing so, and then we managed to prove this compactness of the embedding, okay? And then as an application of this problem, of this result, we have proved the existence of solutions to problems, to equations involving the one Laplacian operator in all of the Rn, okay? Okay, I said you that this paper have inspired us in the present paper I'm presenting to you now. And I can see I can say this because in this paper we have tried, in fact we succeed in showing that the space BL-rad, okay, who is this space BL-rad? It is an analogous of the space BV-rad, okay, but considering higher order derivatives. Then we consider this space as to be the functions in W11 of Rn, okay, such that the Laplacian of U, it is a radon measure. Then we succeed, of course, the BL-rad, it is the space of functions in this space which have a radial symmetry, okay, which is radially symmetric. Then what we have done is we have proved that for n greater than or equal to 3, this space, it is compactly embedded in Lr for r between 1 and n over n minus 1, okay? The first thing that I would like to highlight is exactly this number here, n over n minus 1. Someone could feels a little bit strange, this number, and I to be honest, at the first sight, I also feels it was a little bit strange to have just this threshold rather than n over n minus 2, okay? Because of course we do know that the W11 itself, it is continuously embedded in this space, okay? Then, of course, since we are considering a space which a degree of regularity better than we were in W11, we hoped to find a better better embedding, okay? But this, in fact, the fact that we just succeed in proving that we can have this embedding just up to n over n minus 1, it have something to do with the fact that the space which you have to consider when we are trying to prove that result, it was the space W21 delta, okay, which is because in fact after I'm going to present you this the proof of this theorem, then I'm quite sure that the proof is going to be, this fact in fact is going to be much more clear, but it have to the fact that this space we don't know whether or not it is continuously embedded into this space. Okay, we didn't succeed to find in the literature, and we have tried to prove it. We didn't succeed to prove that this space, it is continuously embedded into the space LQ for Q up to n over n minus 2. Okay, very good. Okay, and then in the second part of this paper, okay, after we proved the compactness of this embedding, we have applied this sort of result to a problem involving the one biharmonic operator, the one Laplacian operator in all of the Rn. Okay, then we succeed in proving that this equation, it does have a non-trivial solution. In fact, it is a ground state solution among that one which are radially symmetric. Okay, and in the nonlinearity F, we have considered the usual conditions to have the multi-pass geometry. Okay, and then we prove this theorem. Very good. This is what we are going to do. Okay, now I'm going to I would like to give you a flavor of what we have done. The first thing that we do in this paper is to deeply study this space here. Okay, the BLRN. Then it is the space of the W11 function such that the Laplacian of U, it is a radial measure. Then we can prove that this space, it is a normally vector space, okay, when ended with this norm here. And now we present a technical result which is used to prove the lower semi-continuity of this norm. Okay, for example, when we deal with this sort of problem, at a first sight, we could think that we should deal in the space W21 delta, the space which I have just presented you. Okay, but for the reason that this norm, it is not lowered semi-continuous with respect to the convergence of the LP space. Okay, this fact together with the fact that that space W21, it is not a reflexive space, which is a subspace of L1 space, we cannot deal with this space. In fact, we have to deal with a relaxed form of the problem, and we have to do it in a bigger space. Okay, and this is the space in which we should do it. But this space, it will be the correct space to deal with this problem just if we are able to prove that this norm, it is lower semi-continuous with respect to the LQ topology, okay, when Q is between 1 and n over n minus 1. But for example, when we are dealing with the one Laplacian operator and we are trying to do the analogous thing to the norm of the BV space, all the things runs smoothly without any problem, okay? But here, since we are dealing with functions which have a greater regularity, we need some kind of regularity result in order to show that this limit, the limit of the function, of the sequence in this space, okay, the limit in LQ space, this function, in fact, it does belong to the BL, okay? And for it, we have to show that the first derivative of this function, it is a distribution generated by an L1 function, okay? And then we have in the beginning very big problems with this, okay, and including I would warmly like to thank Professor Augusto Ponce because he has helped us a lot with the proof of this proposition, because it is very technical and used some techniques which we were not so used to, okay. And then the first technical result which I would like to present, it is this proposition. Okay, this proposition says to us that if you take an n1 function and you just know that the Laplacian of the distribution, the distributional Laplacian of U, it is a distribution generated by a radial measure, then in fact you do know that the Laplacian of U, in the distributional sense, it is an L1 function, and we have this kind of estimate, okay? The proof of it is a little bit technical. I just would like to give you a flavor of it, okay? The first thing that we should do is trying to prove a version of this estimate in bounded domains, okay? Then in the first step, we take in y in a a point in Rn, and then we try to prove that the integral of the gradient of u in a ball R1, it is less than or equal to these integrals in these balls R2, where R2 is bigger than R1, okay? And by using arguments based on the density of the C-infinity functions in that space, okay, which in fact can be proved totally independently of this proposition, okay, it is enough to prove it for C-infinity functions, okay? Then let us take a C-infinity function. Let us gonna try to prove this inequality here, okay? The first step is to prove that if we take R, a point between the median point between R1 and R2 and R2, okay, if we take R in this interval, and V, a solution of this problem here, okay, in a harmonic function which agrees with H in the boundary of the ball BR, then we have this inequality here, okay? In fact, in order to prove this inequality, we have to use a kind of representation formula to V, okay? Since it is a harmonic function, this representation formula does not have an integral in the ball BR, and just it remains the term on the boundary of BR, okay? Where here we have the usual Poisson kernel, okay, which is given by this expression. And then by estimating the gradient of V, which is going to involve the gradient of the Poisson kernel, we can perform some estimates, okay? Okay, now if we take R in this, Now if we take R in R1 plus R2 over 2, okay, and if we take V, a solution of this problem here, 3, which is this one, with H equals to U, note that U minus V, it is a function which vanish on the boundary, and the Laplacian of this function, it is equal to the Laplacian of U, because V, it is a harmonic function, okay? Then this function is going to be a solution of this problem, okay? Then from elliptic estimates, which we can note that, for example, it is not a usual Dirichlet problem. It is a Dirichlet problem with a measured data, because we just know that the Laplacian of U, it is a radon measure, okay? Then by using some elliptic estimates, which we found in the book of Professor Augusto Pons, it follows that the integral of the Laplacian of this function here, okay, which is W in fact, it is less than or equal to some constant which just depends on n, but not on y, okay, times the integral of the Laplacian of U in this ball. And this is the equation 5, okay? Now, from 4 and 5, we have that the integral of the gradient of U in this ball, at the end of the day, it is less than or equal to the sum which we should use in the beginning, okay? Because this term could be majorated by this one by 5, okay? And this one could be majorated by this one by the very first equation, the equation 4, if I remember, okay? Okay, then we just have to integrate the last expression for R between these two numbers, and then we get, rather than this inequality, this expression here, the integral over the boundary of this ball, we have the integral in all the ball, okay? And then in order to prove that this result is still holds for all of the Rn, we just would like to implement some kind of covering of Rn in a clever way, in such a way that we have the global estimate. Okay, very good. The real need of that proposition, it was to prove this lemma here, okay, which is absolutely crucial to all of the argument we are carrying in this paper. If we take a bounded sequence in BL, okay, and if we know that this sequence strongly converges to U, okay, in the space LQ for these values of Q, then this function U, it does belong to BL, and we have this inequality here, okay? This, roughly speaking, is saying to us that the norm of the BL, it is lower semi-continuous with respect to the LQ convergence, okay? Then, by using this last result, we succeed in proving that this space, it is in fact a Banach space, okay? Also, the continuous of the continuity of the embedding of BL in LQ for this range here, okay? And now we would like to prove the compactness of the embedding of BL rad in the LQ for Q greater than 1 and less than or equal, or less than, strictly less than n over n minus 1, okay? In order to do so, it is crucial to prove to have a kind of a version of the radial lemma of Strauss to the space BL, okay? Then this is the statement of the radial, of this version of the radial lemma, okay? I should say that this condition here, okay, of n is greater than or equal to 3 is because of the estimate that we have in the functional u, okay, when we take u in BL rad, okay? You can see that we have to take n greater than or equal to 3, otherwise we will have something which is not useful for us here, okay? Okay, the proof of this lemma, it is more or less following the usual steps, okay? We first prove it for infinity functions, we deal with the function itself, more or less the same steps that we have followed when we done it for the space BV rad, okay? I will skip this proof because it is rather technical and I think that I'm not going to have enough time. Okay, then with this, sorry. Okay, no, sorry, I cannot skip this because it is the proof of the theorem 1.1. Okay, it is the proof of the compactness of the embedding of BL rad into the LQ space. Okay, okay, then let us go into prove this compactness, the compactness of this embedding. Let us take a bounded sequence in BL rad. Okay, then we knew that there exists a constant with it bounds from above the norm of the solution. By the version of the radial lemma of Strauss, we have a kind of, let me say, for example, we have a kind of a uniform control, okay, in the size of un, in the gradient of un, okay? We know that this kind of is estimates, and then we know that both of this quantity, it goes to 0 uniformly with respect to n, where x goes to infinity, okay? Then we can, since r it is greater than 1, this power here, we can take a very, very big ball, okay, br, in such a way that in the complementary of this ball, the function itself to the power r, it is less than or equal to this quantity here, okay? Then if we integrate both sides of that, the last expression in the complementary of br, we have that this integral, it is small enough, okay? And then, of course, since we have controlled the behavior of the sequence outside balls, okay, we just have to apply some kind of compactness of the embeddings of the BL rad in bounded domains in order to get the result. And this is exactly what we have done it here. We have done here, okay? In fact, in the paper, we perform a deeply study of the BL rad space in bounded domains, okay? And then we succeed in proving the compactness of the embedding. Okay, very nice. Now I'm going to present you an application of this result, okay? As I told you, the application is going to be in a quasilinear elliptic problem involving the one biharmonic operator and also the one Laplacian operator, okay? And what we have done here is to implement a variational approach to this problem, okay? Then we have considered the energy functional associated to the functional, and the energy function associated to the functional, it is in fact well defined in the space BL of Rn, okay? And the energy function, it is given by this expression here. We have the contribution of the total variation of the Laplacian of u, the integral of the modulus of the gradient of u, and the nonlinear term here, okay? Very good. Note that this functional can be written as the difference among two functionals. The first one is this one, okay, which is the three first terms, which we have called here the psi naught. And note that this psi naught, it is locally a Lipschitz functional, okay, because this is a norm to the power 1. And the another part of the functional, which comes from the nonlinearity, it is a C1 functional when defined in this space. Okay, then we have that the functional psi, it can be written as the difference between locally a Lipschitz functional and a smooth one, okay, a C1 functional. Very good. Then, for example, we could apply the nonlinear theory, which is suitable to this sort of regularity of the functions, okay? Then, for example, we have people like Professor Zhu-Qiang, Professor Shang, K. Shang, and Clark, which have studied a lot this sort of problem. And as we know, there are, roughly speaking, all the nonlinear theorems that we know, Multi-Pass Theorem, Eklund variational principle, and so on and so forth. We do have a version of this sort of results to functions which have this regularity, okay? Then we say that a functional u is a solution of our problem, or a critical point of the energy functional, is the zero, where this zero, it is an element of the dual of the BL, okay? It is the zero of the dual of BL, okay? This function, this element here, it does belong to the subdifferential of psi 0 minus c prime f of u, okay? But since this is a convex functional, then we can use a different characterization of this sort of subdifferential of this problem. And then we can say that u is a functional if and only if we know that this function, this expression here, c prime f of u, it does belong to the subgradient of c0 of u, okay? But this is the same of saying, it is the same of saying that we have that this inequality, this variational inequality here is satisfied, okay? Then, to resume, what we are looking for is to a function in BL of Rn which satisfies this variational inequality here, okay? Very good. In order to do so, what we do is to prove that the function of psi it does satisfy of all the assumptions of a specific version of the Multi-Pass Theorem, which we have proved together with Professor Giovany Figueiredo in a previous work. Okay. Then the function of psi, when restricted to BL rad, because of course we have to have some kind of compactness, okay, in order to get a critical point of it. Then we have to restrict the functional to the space BL rad. Then this functional, it does satisfy the geometric conditions of the Multi-Pass Theorem. Okay. Then from the in order to prove this proposition, it just roughly speaking, it follows the usual arguments that we are used to. Okay, the very same estimates in general. Okay, then from the Multi-Pass Theorem, we know that there exists a sequence epsilon n going to 0 and a sequence un in this space, such that the energy of this solution, of this sequence, it goes to C, where C it is the minimax value given by the Multi-Pass Theorem, okay, which is given here below. And also that we don't have properly a solution, okay, a critical point of the functional, but we have an almost critical point in the sense that this inequality 16, it is satisfied, okay? Just note that up to this last term, we have exactly what we want, okay? Then the next step is to show that this sequence, it is bounded in BL rad, okay? And this can be done just by taking V equals to 2 times UN in this inequality 16 here, and by using the Ambrosetti-Rabinovich condition that we have in the functional f, okay? Then we sum and rest this term, then we throw it away, the first term, and then we use the estimates that we have on F, and we succeed in proving that the sequence is bounded from above. Okay? Okay, then since the sequence is bounded in this space, we can use the compactness that we have proven in the first part of the paper in order to show that the sequence UN, it converges to a function U in LR when R is a number between 1 and n over n minus 1. Okay? Then since we do have this strongly convergence, we can use the growth conditions on F in order to prove that the integral of UN, it does converge to the integral of f of u times u, okay? And then we just have to deal with the first part of this inequality, because this term, the last term in the inequality 16, we already know that it goes to 0 because UN, it is a bounded sequence. Then when epsilon goes to 0, this last term, it goes to 0. We do know also that the first term on the right-hand side, it goes to the integral of f of u times v minus u, okay? Then we just have to deal with the left-hand side of this inequality. But the left-hand side of this inequality, it does not offer any difficulty because we just have to use the lower semi-continuity of the space BL with respect to the LQ convergence. And then we do have this inequality 19 here, okay? And then we can say that U, it is a solution to this problem, a bounded variation solution to our problem, okay? In fact, we can prove from the inequality 19, we can implement a lot of very technical result, which is based on convex theory, in order to show that the solution U, in fact, it does satisfy a version of the Euler-Lagrange equation associated to the problem itself, okay? But I'm not going to enter into details regarding this issue here, okay? Okay, also, from the convergence that we have got from the compactness of the embedding, we are also able to prove that the functional U, in fact, it is a function in the energy level C. And since C it is greater than 0, we know that this function U, it is not the trivial one, okay? Then what is left to prove? Okay, of course, we just find a critical point of the functional, but just when restricted to the BL rad space, okay? Then, in order to show that, in fact, this inequality here, 19, it is satisfied by all V and BL on BL of Rn, and not for those ones which belongs to this space, okay? We just have to use a kind of symmetric criticality principle of Palais, okay, which we found in a paper from Marcos Quasina, okay? And then we know that we do have a solution to the problem. What it is left to do is to show that this solution, it is a ground state solution among the radially symmetric ones, but this can be done based on a Nehari approach, okay? By mimic the arguments which Giovany, Figueiredo, and myself, we have used in a paper of Milan Journal of Mathematics in 2018, okay? Just by mimic the argument, we succeed in proving this last thing, okay? Okay, then the paper which gives rise to this presentation, it is this one, okay, together with Elard Juarez Hurtado and Olimpo Miyagaki, and here you have some other very important, some papers which deeply inspired us to do this work, okay? Thank you very much for your attention.
Thank you, Marcos, for the very nice talk. And now we have some time for the questions and comments from audience. Let me see if you have something. Until now, you have no question, but I would like to ask again. I asked that already to you, but for the one Laplacian, what the regularity are you expecting to find, or some work that you have that?
Okay. In fact, we don't expect anything better than a BV function. Of course, for example, when we are dealing with equations involving the one Laplacian operator, we do have some situations in which we have find something which is a little bit better than just a BV function. For example, if you have a term which involves the gradient of the measure of the derivative of u itself for example, in the left or in the right-hand side of the equation, in general, these terms tends to have a regularizing effect on the solution u. Then, in general, you have a function of a BV function is still it is a BV function. We don't know if it is, for example, a W11 functional, but for example, in some situations, you can prove that the jump part of the derivative of u, it is equal to 0. Then you don't have any kind of first order discontinuity in the function. But this, in general, it happens just in very, very specific situations. In general, we don't know anything about that. And I think that this is more or less, this is not so strange because, for example, if you look to for example, the eigenvalue, the problem of eigenfunctions of the first eigenfunction of the one Laplacian operator, it is a functional which tends to have first order discontinuity. Then you cannot expect anything better than a BV function in this specific case, at least.
Okay.
João Vitor, né?
João Vitor.
Can we obtain the one biharmonic operator as a limit of biharmonic operators of P Laplacian type? I strongly believe that we can obtain this. I strongly believe, because it will be exactly the same thing that it happens with the one Laplacian operator, because the one Laplacian operator, it can be thought as the limit of the P Laplacian operator as P converges to 1. And in general, there are some people which in general deals with the one Laplacian operator through an approximation procedure when P goes to 1. Then I strongly believe that yes, I didn't prove anything like that. I didn't, but I strongly believe that yes.
Thank you. I don't have any more questions, but for the bounded domain, Marcos, are there already some results for one B harmonic in the one Laplacian operator?
The one Laplacian operator in bounded domains.
The combination of
okay. Of one biharmonic operator and one Laplacian operator in bounded domains. Yes. The combination of both of them, I don't know, but it will not be so. It will not be so many difficult, I think, because if you put, for example, in the paper which I have done with Sara Barilli, we just approach the case of the one biharmonic operator equals to something. If we have, for example, the one Laplacian there, the one Laplacian operator there, we just would have to deal with the norm, the full norm of the space, which the contribution of the Laplacian, the gradient, and the U. It is more or less the same, I think. Mm-hmm. At least with the sign minus. With the sign plus, I don't know.
Okay. Thank you very much again. I believe you don't have more questions on the chat. So we hope meet you again very soon here at UFSCar. So thank you very much, Marcos.
Okay, my pleasure. Thank you very much.
And in 15 minutes, we will have the lecture of Professor Augusto Ponce that he will continue with us in 15 minutes. So we invite all the audience to join us very soon. So bye-bye.
Hello, everyone. It's welcome to the next lecture in the workshop. It is for me a great pleasure to introduce Professor Augusto Ponce from Université Catholique de Louvain in Belgium. He is going to talk about a new type of connected component created by singular potentials. Professor Augusto Ponce has many contributions in nonlinear analysis and partial differential equations, focusing on topics like Sobolev maps into with values into manifolds, and nonlinear PDEs and its connections with measure theory, among other topics. His recent book, Elliptic PDEs, Measures and Capacities, is an interesting invitation to the subject and gives an idea of his research topics. Welcome, Professor Augusto Ponce. It's a great pleasure to have you in the workshop. Thank you for accepting our invitation.
Well, Gustavo, thank you very much for the invitation. And actually, it's an honor to be able to give a talk twice here. It's really a pleasure. And be introduced twice.
Thank you so very much.
So I'm going to thank all the organizers for this nice conference. And it's and I hope I can see you in São Carlos one of these days soon. So let me start with my talk now about a new type of connect components that appeared in the. This is something that we discovered while we're studying the strong maximum principle for the Schrödinger operator. So let me start with what I could call experimental mathematics. Well, you realize something which is quite easy to realize, and then you try to understand how you can generalize and whether there is something more general behind it. So let me start with this case here. We have a continuous function in Rn, and if I assume that this integral here of u divided by x to the power n is finite, then the function u has to be necessarily zero at the origin. And this is completely trivial because you know that 1 over x to the power n has infinite integral on any neighborhood of the origin. So this is the only way of having finite integrals to have this continuous function to be zero. And another case that you can think about, you have a continuous function in Rn. Now, instead of working with a potential like 1 over x to the power n, you have just 1 over x1. x1 is just the first component of x, which is very singular, and but perhaps less singular than the other one. But here you're along a hyperplane, the hyperplane x1 equals 0. Now what happens? Again, you have an integral which is infinite in any neighborhood. 1 over x1 integrate over any neighborhood of the hyperplane x1 equals to 0 has infinite integral. So the only way of having this integral finite is to have your continuous function 0 everywhere on the hyperplane. Okay, so this is very easy. Now let's try to understand whether there is something more general behind. And actually, the assumption that u is continuous, you don't really need that. You can even think about just an L1 function. But of course, well, if you use an L1 function, you might say, okay, but I can change the value of the function at the point, so it becomes meaningless to talk about the function being 0 at 0. So, but the right way of looking at the problem is to think in terms of precise representative of this function u. And what happens that if you look at the precise representative of u at the origin, you can prove that it exists and it's 0 under the same assumption we had before. And actually, it's something very, very simple to realize. Oh, now I have another type in my talk here. So I have twice the proof, so it's a square proof. So here, what happens here? So I'm taking so how do you compute the precise representative of u? Well, you take the integral of u on a ball around the point we're interested in our case is the origin, and I divide by the volume of the origin. So here, okay, it's the volume of the ball. It's like r to the power n. So I divide my integral by r to the power n, and it goes to show that this integral goes to 0 when r goes to 0. Now, what happens here? Because of our assumption, you see, you're inside, if inside the ball, you know that the norm of x is smaller than r. So if it's smaller, and what you can do, you just replace 1 over r to the power n inside the integral by 1 over x to the power n. It becomes larger. But you're integrating on the ball of radius r, and you assume that the integral of the entire Rn is finite, so which means that when you let r go to 0, this integral goes to 0. And you deduce that the precise representative of u is 0 at the origin. Now, let me go to the second example that I had, was a continuous function with this integral finite. Now, let me assume that u is it's a Sobolev function, a nice Sobolev function. Now, the point is that when you are talking about Sobolev function, you can talk about traces. And here you have this hyperplane. Hyperplane is n-1 dimensional. So you can talk about this function on the hyperplane in the sense of traces. And in this case, you understand of u being 0 in the sense of traces. Well, this is one way of doing that. You could try to think in terms of precise representatives, but I'm going to stick to traces in this case because, well, they are available. Now, how do you do that? Again, twice the proof. You take the integral. You integrate your function u on the hyperplane, but not the entire hyperplane. I just take I intersect with a ball, large ball. It doesn't matter the size of the ball. And then you take a function zeta epsilon with the following property. You take it in such a way that it has slope 1. So it's a function which is 0 on the hyperplane with slope 1 on the hyperplane. And then you extend it in such a way that it stays with nice Lipschitz control, independent of epsilon. And then it just fades away when you are away of distance epsilon from the hyperplane. So you see, we start with something which is 0, with slope 1, and then you move back to something which is 0 when you are at the distance epsilon from the hyperplane. Okay, I take this kind of function, so I can estimate in this way. And then I integrate by parts. Now, when I integrate by parts, don't forget that zeta epsilon is 0 on the hyperplane. Now, I integrate by parts. I get a term with gradient of u, gradient of zeta epsilon, and then a term of u and the Laplacian of zeta epsilon. And okay, I put everything in norms or absolute values, so I can get an estimate. And my integral is in a neighborhood. It's a neighborhood of the hyperplane. So I move up to epsilon. Now, my function, I told you, I can make sure that the Lipschitz constant is bounded by, let's say, 2. And the second derivative, you see the function is 0. You have first derivative is controlled, and second derivative, well, you can't expect it to have uniform control because you want it to become 0 after x1 becomes greater than epsilon. So you can make sure that your second derivative is controlled uniform in terms of 1 over epsilon. Of course, it's going to blow up as epsilon goes to 0. But you're shrinking your region. Now let's go to this integral here. You have gradient of u. Zeta epsilon is uniformly controlled. So when you let epsilon go to 0, this first part is going to 0 when you integrate. And then you have u Laplacian of zeta epsilon. Laplacian of zeta epsilon is controlled by c over epsilon. But epsilon is like distance to, is the nicest case of distance from the hyperplane. So this term you can control by a term of u divided by the distance to the hyperplane, which is x1 in this case. And you know that by assumption the integral of u over x1 is finite, which means that when you let epsilon go to 0, this term also goes to 0, and you deduce that the trace of u is 0 on the hyperplane. Okay, so these are the case sort of warm up for the problem. Now, what I want to understand is how to identify the common zero set of all Sobolev functions in Rn under this assumption. Now, what is V? Well, V is just a Borel function. Just a Borel function. I don't assume anything more than that. So it's a function with values between 0 and plus infinity. It could be plus infinity in large sets. So if you look at the the extremal case, like you have V, which is identically 0, have no condition whatsoever, so you have any W11 function. So of course, you cannot talk about a unified 0 set. And the other extremal case is V plus infinity everywhere, which forces your function U to be 0. Okay, so there's just one function, the function is 0 everywhere. So these cases are easy to handle. And I want to understand the case of a general Borel function and whether it can identify neatly the 0 set of all Sobolev functions. This is my goal here. Okay, now so V is given, capital V is given, and you want to understand what's going on for all functions in the Sobolev space. Now, let me explain the setting. So it's I asked the question in Rn, but of course we can. It may be more convenient to work on a smooth bounded open set because, well, it's nicer to work there, and once you understand on a domain, then okay, you just let it go away. You just take domains larger and larger, and then you get information about Rn. So this is. So I'm assuming I'm going to stick with a nice domain. The Borel function is fixed as well, and from time being, actually, I'm going to stick to this assumption as well, and then at the end I'll come back to this later. I'll be assuming that my function is not W11 but W120. So I'm taking W120 functions. I'll explain that what we can do later if this is not the case. Actually, we don't know. And I'm assuming that's L2 of V. Now, this is to simplify a little bit the notation. It means that U squared times V is an L1 function. So V is the weight, and I'm assuming it's L2, U is L2 with respect to this weight V integrated with respect to the Lebesgue measure. So this is a Hilbert space, and this is a Hilbert space with respect to this inner product. You see, this is the part that is that behaves well with the Sobolev part, and L2 of V, you have this part which is well for the L2 V part. So this is an inner product. And now, very important notation. Now, the main tool here you're going to use is you're going to take the minimizers of this functional here. So I'm given, I fix an L2 function on the domain, and I take the minimizer of this function. So here you have it's just the norm of U square in our Hilbert space. And then you take minus U times F. So everything is well defined, nicely defined. You have this thing which is quadratic. This is linear with respect to U. And you can minimize without any problem. So the minimizer exists. This is very standard in calculus of variation. Just by the direct method of calculus of variation, minimizer exists. It's unique and very easy to get the Euler-Lagrange equation because you have just a second-order polynomial. Have the Euler equation, which is a linear equation. See, zeta f satisfies this. This is the inner product is equal to integral of f times v for every v in our Hilbert space. Now, the kind of reaction you should not have in this case is say that, well, if you know that V is in LP for P bigger than 1/2, then W0 and 2 is injected into L2 of V. Okay, don't do this. Because I'm assuming that capital V is just a Borel function, so I'm not interested in this kind of information. And we're not going to use that, so let's put it aside. Now, our Euler equation is linear. There's uniqueness of a solution, so it's very simple to see that you have this linearity of the minimizer. So if you take two data, f and g, and you take scalars, you have this behavior with respect to the minimizers. And another thing which is very standard, you have the weak maximum principle. If you know that f is non-negative, then zeta f is non-negative. The proof is very standard. Just plug in the negative part of zeta f as the test function. And then with the assumption that f is non-negative, you deduce that the zeta f minus the negative part is 0. So, okay, very standard as well. Now, if you combine both, you realize that if you assume that f is L infinity, then you have this estimate of all minimizers. You see, all minimizers are controlled by zeta 1 with a constant, which is the L infinite norm of f. It just follows from this. And here you get an important information from that. You get a very important information. You see that whenever zeta 1 is 0, all zeta f's are 0. All of them. So you have something which goes in the direction you want. You see that you'd like to find a common 0 set for all Sobolev functions. At least you found one for the minimizers. The minimizers, they have this 0 set of zeta 1 as a common 0 set. Of course, zeta f could be 0 elsewhere, but this is a common ground for all of them, and this is the best one can expect for all of them, because this is already the minimal one for zeta 1. But then you have, if you think a little bit better about this, you realize that it works not only for all minimizers, but for all Sobolev functions in the class we're looking at. All of them. Not only for the minimizer, but all of them. And the reason just follows from the Euler-Lagrange equation. You see, the Euler-Lagrange equation has a lot of symmetry here. So actually, if you plug in the Euler-Lagrange equation, 2 minimizers there, you can play around and just get the information from the integral there. So if you combine them, just playing one minimizer with another one as a test function, you get this kind of identity. So you have, in this case here, what I want to show is that zeta of chi-s is 0. So chi-s is the characteristic function of this set, zeta 1 equals to 0. And what I pretend is that this is 0. This function is 0. So this is the minimizer. And it follows from the Euler-Lagrange equation, because, as I said, if you write your Euler-Lagrange equation like zeta chi-s times 1, is the same thing as the integral of chi-s zeta 1. Same thing, just playing with the Euler-Lagrange equation. But S is defined as the set where zeta 1 is 0, which means that this is 0. And, well, zeta chi-s is a non-negative function with integral 0. Okay, so it's 0 almost everywhere. Okay, this is the first information. And now what I'm going to explain now is that if you had one function u which does not vanish on the set S, then actually you get a contradiction with this information. I'm going to explain you why is that so. Well, if you have one function u which is non-zero on the set S, you can always take the absolute value and you don't leave this space. So you can always assume that it's non-negative. So assume that you have a non-negative function which is non-zero on S. And then you do the following. You take the energy function associated to chi-s, compute at t times u. T is just a real number. And you get t squared times something positive minus t times the integral of u. Now, if t is very small, close to 0, well, this is t squared. T squared is much smaller than t. So you have this sign here that dominates, comes from the integral of u, which is non-zero because I assume that u is non-zero on S. So I realized that the energy function is negative at some function, which means that this infimum is negative. Well, the infimum is given by zeta chi-s, and which means that it cannot be trivial. So you get a contradiction from that, and the contradiction comes from the fact that I assumed that there was some function which did not vanish on S. So you understand now how you get this contradiction. Okay, but you have this information that all Sobolev functions vanish on set S, but well, it's a little bit disappointed as a matter of fact, because if you go to assume that V is L1, which is already quite nasty for people who like to live in the invariational setting, you don't have the nice Sobolev embedding that I mentioned. In this case, this comes from, it's not quite Trüdinger. Trüdinger, he got a first maximum principle, strong maximum principle in this case of V in L1 for the Lebesgue measure. But then this was improved by Ancona, who proved that actually the set where solution vanish, they must have, the minimized vanish, they must have 0 capacity. Now, the zero Sobolev capacity, I'll give you I'll recall the definition of this capacity in a moment. But it says that the dimension of S cannot be larger than n minus 2 in this case. And this is Well, it means that it's negligible for the Lebesgue measure, which means actually that the result I just showed before, it's useless because we already know that S is negligible. So saying that U is 0 on a negligible set, it's meaning, well, it doesn't say you anything. So this is not good for us. I mean, the previous result is not good for us because of this. And if you take a smooth function, and you assume, and you take as a potential 1 over the distance to the boundary with a certain power. And then you can show that if alpha is greater than or equal to 1, the set S is the boundary of omega. So again, it's a manifold of dimension n minus 1. It's negligible for the Lebesgue measure. Okay, this is very bad. So it means that the previous result doesn't say anything in this case as well. It's an empty statement. So you see, it's everything here is undetected for the Lebesgue measure. But what happens that the second one, it is detected if you use the capacity, because the capacity doesn't see sets up to dimension n minus 2. Everything that is above dimension n minus 2 is seen by the capacity. So this example is actually seen by that. If you look at the capacity of the boundary of omega is positive. In that case, it's 0. And actually, you don't expect better things from Sobolev functions in W1, 2. But I'll come back to this in a moment. But if you want to get something better about zero set of Sobolev functions, the first thing is to give a better definition of the set S. The one I gave you was a little bit lousy. And the first observation is that zeta f, the minimizer, any minimizer with bounded data, can be defined very nicely. And the reason is the following. You can show that zeta f, if you take non-negative data, non-negative bounded data, you can always show that the Laplacian of zeta f satisfies this relation in the sense of distributions. It says that this is an L1 function, this is very nice, so you can prove this kind of thing. Now, if you think in terms of zeta f as a function, it means that you have the contribution, you have a sort of Newtonian potential that comes from f. Now, if f is bounded, Newtonian potential is a continuous function, so you have a contribution that comes from f, and then everything else comes from something which is negative. You see, you have this less than or equal to, this is negative. So actually what happens is that a minimizer with non-negative data can always be written as a continuous function that comes from the Newtonian potential from f, and what remains is a bounded subharmonic function. And well, bounded subharmonic functions, they have very nice property. Well, subharmonic functions, you know that the averages around points, they're monotone. And if it's bounded, it means that the average converges when you let r go to 0. And since what's left is continuous, you know that this limit always exists. And this is what we call, this is a precise representative, and you can show that it is precise representative of zeta f. And it's defined at every point of omega. Every point, there's no ambiguity. You don't start to complain about, well, if I take another representative, no. This is perfectly well defined at every point. And I'm going to use this one to define my set S. So I take the precise representative associated to zeta 1 and define S to be the 0 set. So it's perfectly defined. And then you can just show that if you look at any precise representative of zeta f with bounded f, also satisfies, is also 0 at S. And it's very simple. Just take the inequality I showed you before, take the average, pass to the limit, you get this relation at every point. In particular, whenever zeta 1 hat is 0, zeta f hat is 0, so you have this information. Now, how do we move to general Sobolev functions out of this? Because, well, they are defined almost everywhere, and you still have some problem about that. But actually, you can do something much better than this. It goes back to Feder and Zimmer, where they proved that NW12 function is very nicely defined, except on a set of W12 capacity 0. Now, nicely defined, what do I mean by that? It means that they have a precise representative at every point except for a set of 0 capacity. Now, what is the capacity? Okay, the capacity of a set, a compact set. you just take the Sobolev norm, W12 norm, take the squared, and you minimize this with respect to all functions with compact support which are bigger than 1 on K. And as I said, you have this dimension n minus 2, which is it separates set between the condition of being capacity 0 and capacity positive. It's a sort of threshold. Everything with dimension is strictly less than n minus 2 has 0 capacity. If you have something which has dimension strictly greater than n minus 2 has positive capacity, and dimension n minus 2 have to check. It's a little bit tricky. But you have this information. So you see that these functions that are nicely defined, except for sets that are of dimension n minus 2, if you want to think about in terms of dimensions. And then you can prove. You have to think a little bit better, but it's more or less the same kind of trick that I showed you before for Lebesgue, is that if you look at the precise representative of U, it's 0 quasi-everywhere in S, which means except for a set of 0 capacity. So now you get this is the best we can hope for, because a Sobolev function cannot be typically better defined than outside of sets of 0 capacity. So you cannot expect anything better than this. So this is the best we can hope for. Now, of course, how bad can set be? And the answer is very bad. And very bad. Just take any closed set in omega, any relatively closed set in omega, and you can cook up, it's not very difficult, just cook up a potential V such that whose set S is equal to F. So there's a way of finding a V in such a way that the set S coincides with the set you fixed from the beginning. So it means that it can be very rough, the set S. There's no hope for any kind of regularity of S whatsoever. Now let me explain you now how can we move forward to get some better information about what we can say about Sobolev function in W12 intersect with L2 of V. And this is related to the problem we start with. What I'm showing you now is sort of things that you realized afterwards. It wasn't the problem we were looking for. You were interested. This is a work with Luigi I'm talking about. And you were interested in the strong maximum principle. This is something that appeared recently in 2020. And what we proved in this paper was that, whose reference I'll give you at the end, it's you can always decompose omega minus S into finitely or countably many disjoint components. And these are the components I was talking about that I mentioned in the title of the talk. They come from the strong maximum principle that we are looking for. So here in this case here, you have the set S and you have 4 different components. And if you know, for instance, that set S is closed, well, the components are the connected components in the usual sense, but the set S need not be a closed set, so you have to be a little bit careful and how to do things here. And actually, I said something which is not quite right, because the components need not be exactly, did not coincide with the connected components. There can be more things, and I'll give you an example. There can be more than the standard connected components, even if S is closed. You have to be careful about this. So this is not, it was not correct what I said. It can be nastier. But you have these components, and I'll explain in what sense they are components of omega minus S. But the important information, this is how the strong maximum principle enters into play here, is that, take for instance this component D4. Take D4. If you have datum, bounded datum, which is non-trivial positive or non-negative in D4, then zeta F, the minimizer, is strictly positive in D4. So you see, if it's non-trivial in D4, it's strictly positive. So it's a strong maximum principle in each component separately. And if you know that F is 0 in D4, it has to be 0. If F is 0 in D4, then zeta F is 0 in D4. So what happens that, so the minimized, they behave completely separately from each other So what we proved that it's to have the strong maximum principle. It holds not inside every omega, but inside each component of omega. Let me explain you what's behind here, and to explain how these components they pop up from the problem. And actually, it's related to a notion of dual solution that was introduced by Maluz and Orsini in 1996 that goes back to a similar representation by Stampaki in 1965, is that you can represent these minimizers pointwise. You see, you have the precise representative pointwise as integration of f with respect to a function gx. So you see, x is fixed. There exists a function gx such a way that this formula holds forever f. So you see, in particular, if you have x that is in S, you know that this is all 0, gx is 0. So gx is 0 whenever x in S. But if you take a point which is not in S, a component, and you look at the set where gx is positive, it coincides with the component. So this is a way of identifying the components in terms of this function gx. So you see, if you take a point in component D4, you look at gx associated to the component D4. So gx is positive everywhere in D4, and it's 0 everywhere else. And same thing if you take another point in D1, D2, and D3. So this is a way of identifying these components in terms of these functions gx. And there's a nice consequence of this fact. If you multiply, and this is something which is not obvious actually. It follows from our theory. This was a lot of work to get, but once you know this and you look at this formula, this dual representation of the minimizer zeta f, you realize that I told you that you have linearity of zeta f, but you have a sort of nonlinear linearity of zeta. In the sense that if you multiply zeta f by a characteristic function of a component, you can move the characteristic function inside the index. So you see, the chi di, if you have a constant, you can move the constant inside, but you take the chi di, you can move inside. It's just a consequence of these two facts. But I'm not going to enter into the details because I have only 10 minutes left. You can. This is a simple exercise. But another thing that you can get from these components is that you have a very, very nice property. And because, well, these components are not only related to the strong maximum principle, but they also relate to existence of distributional solutions. For instance, take a point in D4. Take a point in D4. If you know that this function, the function gx naught, if you know that gx naught, which is a Green's function, if you know that it's a Green's function in the sense of distribution, which means that take minus Laplacian of gx naught plus v gx naught equals the Dirac mass at x naught. If you know at some point gx naught satisfies, for x naught, some x naught, this equation is satisfied, then if you take any point in the same component, the gx associated satisfies the same equation with delta x. So once you know that you have a distributional Green's function at a point, you know that for any other point of the component is also Green's function in the sense of distributions. It's something which is very nice that is given by these components di. So it's not just something about maximum principle; it's something about also existence of distribution solutions. And of course, if at some point you know that you don't have a Green's function, it means that it doesn't work for any point in the component. So let me show you an example to show you more concretely how it works. Take a ball centered at the origin, and take the potential 1 over x1 to the power alpha. You see the first example, the second example I gave today, with alpha, it was with alpha equals to 1. Here I take any alpha. Now what happens? If your alpha is strictly less than 1, your S is empty. But if you take alpha greater than or equal to 1, the S is the hyperplane. Is the hyperplane x1 equals 0. And then your domain splits in two pieces. You have D1 and D2. And you might ask, what happens to existence of Green's function associated to the Schrödinger operator minus delta plus V? Well, you might think, okay, the larger alpha is, the worse is the potential, so it's less probable to have Green's function. It's the contrary. Actually, if your alpha is between 1 and 2, you do not have Green's function at all. They are not in sense of distributions. And it's completely hopeless. You have no super solution for this problem in this range of alpha. No super solution at all in the sense of distributions. But if you take alpha greater than or equal to 2, then you have the Green's functions for any point that you take either in D1, D2, doesn't matter. So you have plenty of Green's function for each point in D1, D2, and as I explained, on S, it's hopeless, but you have Green's functions in the sense of distributions on D1 and D2. So you see that you can have stronger potentials, and it's more likely to have a Green's function. Now let me go to the problem I started with, which was what you can say about Sobolev functions in omega, and the point is the following here. It's something which is very nice. As I explained to you, if you take a function in the W120 intersect L2 of V, you know that U is zero on S. And then, of course, what's left is the union of the components di. And you can write U as the sum of U times the characteristic functions of di's. Okay, so this is not a big deal. This is completely trivial because we already know that U is zero on S. But here's the important point, which is far from obvious, is that U times characteristic function of di, each one of these functions is in the Sobolev space W12. This is far from obvious. Well, you say, okay, but we know that U is zero on S, so it should work from trace here. But don't forget that I told you that S can be very nasty. It can be any closed set. So there's no hope of having a trace theory to help you with this issue. So this is something which is far from obvious, since S can be anything whatsoever. And the ingredient to get this is that relation that you can move the characteristic function inside zeta. Let me show you briefly how it works. So our goal is to show that U chi di has a gradient in L2. This is the goal. And you can do this. You can see that you can do this by the Riesz representation theorem. So how does it work? Well, if you take any C infinity function, if you know that this integral is bounded by phi times L2, then the Riesz representation theorem for L2 function says that you have the gradient of U in L2. And how do you prove this? Well, actually, it's very simple once you know that relation I told you about the minimizers. You see U here as the test function. So if you look at U as a test function, you look at the Euler-Lagrange equation satisfied with that chi di divergence of phi, you have this relation, and you move the chi di outside. As I explained, you can do this for chi di, and you have the inner product with this chi di. Now, if you write in terms of integral, you're just taking the integrals over di, and then you can use Cauchy-Schwarz. You have integrals on norms of di, and then you just go to omega, which is even larger, so it's even better, and you end up with the norms in the Hilbert space, the full Hilbert space you have from the beginning. And then it's a very simple exercise to realize that a minimizer satisfies the estimate. If you look at the norm in the natural space here, it's controlled by phi L2. It's a very simple exercise, and then you get the estimate you want. So you see, it's but of course, the hard part was to get the relation for the minimizers. So what about these components di? There's something strange, because I told you these components, they appear as Green's function, as the positive sets of Green's function. It's a little bit weird to have a PDE behind, but actually don't need a PDE once you know there exists. Actually, it's you can recover them in a totally topological way. You don't need to go to a PDE to find them. actually. You can do this in a purely topological way. And let me explain how it is. So actually, the potential V you have here, it's already encoded on S. And you have, once it's encoded in S, the way the DIs, they pop up, it's completely independent of V. All the information is already encoded in S. So let me explain. You have this notion of a Sobolev open set. This is something that I introduced with Luigi Orsina in our paper in 2020. And what's in the Sobolev open set is the inverse image by a Sobolev function of an open set. Okay. So you see, so open sets are inverse images of continuous functions. Sobolev open inverse image of Sobolev functions. Okay, so this is an example of a Sobolev open set. But here's a point. You can have this point here in the center, for example. So this is our set here. Even if you add this point here, it is still Sobolev open. It's not open, but it's Sobolev open, even if you keep this point inside. Every open set is Sobolev open, but you have sets which are Sobolev open, which are not open. And once you have a notion of openness, you can talk about connectedness in the usual way. If you take a set and you can split it as a union of two disjoint Sobolev open sets, it's not non-trivial, it's not connected. So being connected means whenever you have a disjoint union of Sobolev open sets, one of them must be empty. So here I have an example. And for example, in this case here, this is a Sobolev connected set. You see it's connected by here. The two pieces that are there, they are pretty well connected because you have here at this point here, they're very well connected. But here, if you take this set as this part here, and you add that one, this is not Sobolev connected, even if you have this point in there. You see, this is something that I mentioned at some point that was wrong. You see, this set is connected in the usual Euclidean sense, but it's not Sobolev connected. And the point, the fact is that the point of contact here is too weak. It's like you can separate them because they are very weak with respect to Sobolev. So that's the point. You don't have enough contact. Here you have enough contact. Here you don't have enough contact between parts. Now, can you have components? Well, can you make sure that you have components? If your set S is very small, how small it is, if you have if the Hausdorff dimension of n-1 is 0, then it's Sobolev connected. You just only have one component. But you see in this case here, this is something that was proved by Van Haftingen and Willem. But if in this case, for instance, you see it's important to see if this point is there. You need to know precisely where the points are located. You need to know every single point of S counts. Here you see if you remove this point, it's connected. If you keep this point, it's connected. Here it doesn't matter. It's important to have a nice criterion to decide whether a point is in S or not without relying on PDEs whatsoever. And there is a very nice Venus criterion that recently approved with Nicolas Wilmet. And it's based on a Venus criteria of Dalmaso in Moscow. And what happened, we realized we managed to connect their setting with our set S. And actually we can identify completely a point in S without a PDE just by looking at capacity, like in the Wiener classical problem. This is the capacity. I'm not going to enter in detail because I'm almost out of time. So if you know that this integral is infinite for epsilon sufficiently small, then it's in S, and you know completely how to characterize this. Now, less transparency here. So, and everyone can go home or can stay at home, but without computer. There's something that we don't know, and it's very interesting. And I told you during all my talk, I was focusing in the case of W12 functions. And what happened to other Sobolev functions? Well, actually, this is the point. The function we're working on were in L2 of V. The L2 of V is not important. L1 of V is good enough. Why is that so? Because you can truncate them. If you have an L1 function, L1 of V function, you truncate it, is L2 of V function. So everything is nice, and you can work with truncation past to the limit. But the problem is that if you truncate a Sobolev function in W11, well, it's still in W11. It doesn't get better. So this is the point. If you have a function W1p, you can still have this decomposition, and you can still say it's W1p as long as p is greater than or equal to 2. You have no idea whatsoever what to do for p between 1 and 2. We don't know how these components are behaving. We don't know if you take a W11 function, legitimate W11 function, whether this is going to be true or not. We have no idea. If anyone has some idea, I'll be very glad to discuss about this. And how these components behave with respect to p, we have no idea whatsoever at all. Everything here is stuck to p equals 2, because that was our approach. So these are the reference, these papers that we focused on. So the paper with Liu Jiaxin about strong and maximum principle, and a recent paper with Stefano Buccheri and Liu Jiaxin will have this decomposition of Sobolev functions in L2V, and more recently, still in preparation with Nicolas Ouimet, the Venus criteria to identify the points in set S. And that's it. Thank you very much for your attention, and you deserve some rest after 3 days of conference. Thank you very much.
Thank you very much, Professor Augusto Ponce, for your very nice lecture. Thank you so much for trying again to deliver your talk. You have succeeded so very well. Thank you. Let's see if we have some comment or reaction from the audience. I would like to ask you about the W1P theory, Augusto. You just talked about it. Perhaps you could talk something about the higher order theory or something in this direction. What would you say, please?
I have no idea. Everything has been done to W12. We have no idea what happens, for instance, the fractional case, or no idea. For higher order case, we have well, as long as you can move to W12 is fine. That's what happens for p greater than 2. If p is bigger than 2, well, it's contained in W12, so it works. But as long as you miss the case W12, you have no idea what happens. It's very frustrating that we don't know how to do it. But the problem is that it's very variational, our approach. It would be interesting to find another way to tackle this without relying on this. Or perhaps someone can find a very tricky idea to approximate W11 functions by W12 functions, still in the same space. This is another way of approaching it. I don't know. And there's also the question about how these components behave. Because if it's because we could look at I mentioned to you that this the way the Sobolev open sets are defined are with respect to W12. Of course, we could define Sobolev open sets with respect to the other W1P, and it would be interesting to see differences in this case. As you move p to 1, there could be some sort of merge of sets, and you have larger connected components. I don't know. Actually, when you move p downwards, you have more connected components. You could have more connected components. I don't know.
Very interesting questions and much work to be done. Huh?
Yeah.
Nice, Professor Augusto Ponce. We can see many greetings, reactions from the audience regarding your very nice talk. Thank you for sharing with us your comments. And I would like to thank you so very much, Professor Augusto, for your patience and for accepting the invitation to give your nice lecture in your workshop. Thank you so very much.
Thank you very much.
Thank you. Bye-bye. Okay, dear colleagues, students, and friends, we are close to finish our workshop. Professor Olympio Miyagi could not attend for this moment and asked me to say some few words at this closing stage. What I would like to say is many thanks. Many thanks to all the speakers for having accepted our invitations. Our great speakers in this workshop were the following professors: Andrei Zulkin, Augusto Ponce, Boyan Sirakov, Claudiano Alves, Davi Arcoia, Denis Bonner, Ederson dos Santos, Eduardo Teixeira, Giovany Figueiredo, João Marcos Duó, Lúcio Bocardo, Luigi Orsina, Marcos Pimenta, Manuel Dalpino, and Patrizia Pucci. Thank you so very much for the excellent lectures you delivered in the workshop. I would like to say many thanks for all those who joined us along the last 3 days in the workshop, and also to those which will see the recordings afterwards. Also, many thanks to the scientific and local committees, with special thanks to Gustavo Mauricio, the man behind the scenes in the workshop, for all the technical support. And finally, I hope to see you personally, hopefully personally, next workshop. Thank you so very much. And since we are still under the effects of the pandemic, please let us kindly ask you to keep yourself and your family safe. Thank you so very much. Bye-bye. See you.